Good morning. We'll be starting off our final day of QCrypt with an invited talk. Yu Chen is going to tell us about quantum computing at Google. Thanks.
Great, thank you. Good morning, everyone. So thank you for all of you to coming here for my talk in the early morning. And also, I'd like to thank the organizers to inviting me here for this wonderful conference. So my name is Yu, and I'm a research scientist working in Google Quantum AI Lab. So today, I'm going to tell you the activities we have been doing in terms of quantum computing with superconducting circuit in our lab. Of course, nothing can be done without a wonderful team. I'm really standing here speaking for a group effort for more than 30 people. These two graphs show here. It contains the hardware team as well as the theory team in LA. And we are located in this beautiful city called Santa Barbara. We're famous. The city is famous for good weather. We're ranking #1 in the United States and good scenery. As you can see, we have facing the sea and next to the mountain. And the office is right there. All right. So in terms of science, what we're trying to do in Quantum AI Lab, of course, the ultimate goal is to build a fault-tolerant quantum computer if you have really large sizable system, and with arrow, that is not enough. Let me switch to a different one. This is really hard. Once you have that, you can think about you can do everything you really want. However, this may take us a really long time to achieve that if it's not too long. That's why we set some near-term goals such that we can achieve as some stepstone towards that goal. We will try to achieve the so-called quantum supremacy, hopefully sometime soon, which we're trying to do something, even though it could be very useless, but that will take classic computer quite some time to finish. And we're also spending a lot of time trying to figure out what are the near-term applications we can try to run on those chips we're trying to build. Of course, this is not just by us. I would say this is a global race for different technologies, and this including us, quantum superconductors, and many others. I can easily name a few of them, such as atoms, spins, ions, and optics. And finally, in Google, what we have been focusing on is superconducting circuits, as I'm showing here. A quick one-on-one, what is a superconducting qubit? A superconducting qubit actually can be understood in a very simple way. It's nothing but a harmonic oscillator, which is something you learned back even into undergrad. So you can think about just as a capacitor, which is formed by this covalent waveguide, highlighted as red here, and an inductor. In this case, it's a little bit special because it's tunable, which is actually formed by this little region where I zoom in here, and this is formed by this special component in our circuit called Josephson junction. And Josephson junction is nothing but two superconducting leads sandwiched by this very thin barrier of insulators. However, this Josephson junction has a very nice property. It's tunable, think about as an inductor, and also it introduces nonlinearity into the system. Once you introduce nonlinearity, the harmonic oscillator has evenly spaced energy levels. Now it has become no longer even. Once you have those non-evenly based energy levels, you can address individual levels individually. Now you have a qubit. So it's as simple as that. And superconducting circuit also has a lot of other advantages other than simplicity. It's very easy in terms of integration, because we are simply built nothing but the integrated circuit itself. And also, if you design things just right, you can put everything right around a few gigahertz. This is in the microwave region, so you can actually control them easily, just simply by the off-the-shelf microwave electronics. And finally, given the recent progress in terms of coherence, now we have a relatively good coherence to gate time ratio. Within the lifetime of the qubit, you can actually run a few thousand gates. And also, one main thing I really like superconducting circuit is that it has a lot of flexibility in terms of design and fabrication. And even in Google, we are actually pursuing 3 different platforms, the so-called XMON, GMON, and FluxMON. XMON you can think about as qubit with fixed coupling, and GMON you can think about qubits with tunable coupling, And finally, Fluxbound, you can think about tunable qubits with tunable coupling as well as more complex connectivities. So I have said a lot of good things about superconducting qubits. So let's go back to think about how can we actually scale up, back to this scaling up map. So I like to say, even back in 2015, we already have demonstrated we can build a 9-qubit chip. And we have achieved low enough errors in terms of gate, such that we can demonstrate a very simple error correction algorithms. And with all the good things I told you, you might think, okay, in order to scale up, things might be relatively straightforward. You just keep moving along this line, you just increase the number of qubits and reducing the error, and you're good to go. This may be one of the reasons you keep hearing this good news. IBM got 50 qubit, Intel got 49 qubit, and Google eventually got 72. This is really exciting because this makes you feel quantum computing is really coming. All right? However, I'm a hardware engineer. So to me, what's important is not those exciting headlights. What's more important is actually the challenges during this scaling up process. In fact, we are facing a lot of problems because we never built such a big system in the past. It's not very clear what to do in many of the problems here. No matter if you move along this x-axis in terms of increasing number of qubits, or we try to reduce the error, or looking for near-term applications. In fact, we never control such a large system. We used to go with few qubits, now we go to tens of qubits. We have to work right on the edge of science and engineering. In fact, internally, we never call ourselves research scientists. We always call ourselves hardware engineer. So what are the challenges we are facing? So let's first move on along the x-axis when we try to increase the number of qubits. When you try to increase the number of qubits, in fact, it's not so hard if you're just simply trying to design a bigger chip and redo the design of the qubit. That is not too difficult. However, what's more difficult is trying to figure out how to use it. The reason is that all the technology in order to control such a system with a good fidelity does not exist. So you have to, in order to increase the number of qubits, you have to actually develop all the technology in order to control such a system. What are the technology we need? It's not just one or two. In fact, it's a full stack of everything, containing all the way from room temperature control software and electronics all the way down to the chip level code in the fridge. In fact, this is what we have been focusing on most of the time in the last 2 or 3 years. And we have to actually abandon a lot of old technology we have been using like 10 years ago. To give you a better feeling what happened, so for example, for the control software, we no longer doing those like academic lab, what we have been doing like just 3 years ago. Everybody has its own code bases. You can never use other people's code, or you can never touch my code. Now we have a group shared code bases. It has thousands of lines of code, and we constantly on the code review and automated test. And more importantly, those codes are maintained by professional coders, and this ensures our code is of high good quality. And given this high good quality of code, that actually allows us to do something we feel it's pretty cool. Instead of doing manual bringing up of this individual qubit, which you can imagine you can try to do with just a few qubits. But when you move to tens of qubits, you really wanted to do things automatically with just computers. So this is what we do. We have something internally called Optimus, which we can automatically run qubit calibration. By compute itself, it runs the calibration, look at the data, and update the parameters. This allows you to calibrate a system up to tens of qubits. And move down in the line, we have spent a lot of time upgrading everything, including control electronics, wiring, and packaging. As the one I show here on the left, we have upgrading our control electronics to much denser control crate. As the one I show here, with just one crate here, you can actually have more than 100 channels. So you can imagine with just maybe 3 of such a crate, you can actually have enough control channels to control more than 50 qubits. So this is great news. And if you look all the way to the right, we have been working with Janice to really make upgrading our fridge. Now we have much bigger fridge than the past. And this with such a bigger fridge, and we can actually install more than 300 coax cable inside the fridge. And finally, we also have spent a lot of time developing packaging for the qubit. such as now we have moved to PCB technology-based packaging, which allow us to have denser connections, as the one I show you here, and that also reduce the crosstalks. And finally, get down to the chip. That is the thing actually we spend most of the time on, is we improve the fabrication process and design. Now all of our qubit platform, all the three have moved to the flip chip technology, where you separate the qubit chip, which is a high coherence, from the no coherent control wiring chip. We have also spent a lot of time developing advanced components such as L-bridge crossovers, or those like complex wiring in order to reduce the control crosstalks. However, increase the number of qubits is not end of the story. What's more important is to make sure you can actually keep reducing the limiting error of your system, because that's limiting the performance of the chip. This is, in fact, the reason we actually want to we propose this quantum supremacy algorithm. For the detail of this algorithm, I will refer you to read this paper we published on Nature Physics earlier this year. But this algorithm can be understood in a very simple language. Just imagine you have a certain number of qubits, just run a certain random set of gates. You can randomly select from the Clifford and non-Clifford gate set. And then once you run it with certain depths, and then at the end of the sequence, you just measure the outcome. This might take you a second to run on the quantum processors. And what you have to do next is to compute what is the expected outcome from theory. This, if the system is large enough, that might take you a while. But at the end of the day, you take the experimental outcome with theoretical prediction. You can compute the correlation between these two in terms of cross entropy. Once you keep increasing the size of the qubit or the number of the qubit, now at some point, it will take even a supercomputer forever to finish to predict what's going on. At that moment, you can claim quantum supremacy. However, what's more important for us internally, we feel this probably is the simplest algorithm. You can try to check the fidelity of your whole sequence or the whole system at this system level. So this is a great for us to try as a first application. So let me give you a quick flavor what is going on. You can refer to this paper we published earlier this year. We run on a 9-qubit Gmon chip on this sequence, as a pulse sequence I show you on the right. Imagine you just punch a photon through pi pulses, and then you can turn on those random gate set, no matter it's in terms of detuning or in terms of turning on the interaction randomly. At the end of the day, and then you just measure what is the outcome of this gate sequence. And here is some examples of data. The blue data, blue bar are the data, and the green dot are the theoretical predictions. And the 4 different plots represent 4 different instances, or you can think about just 4 different random sequence of gates. And you can see that even after 10 cycles, with, like in this case, 5 qubit, you can see we can still have a pretty good matching between theory and the experiment. Now what you have to do is take all these data and then compute what is the correlation between these two, and you can get to this plot, which is cross entropy, both in terms of number of cycles, gate cycles in the x-axis, and as a number of qubits for different color data. And then what you can do is you can just fit for those curve, and then you can put out what is fidelity of the whole sequence. From that, you can estimate what is error you have, say, per qubit and per cycle. And what we found out for our system is around 0.3% error per qubit per cycle. And this actually is pretty good, and we are very happy about it. Of course, we are not just satisfied with a few qubits in a linear geometry. What we have been focusing on is actually build a more complex system. This is the reason we announced Bridgestone Cone. You might have heard about the news earlier this year in APS March meeting. It is a 2D grade of nearest neighbor coupled qubit array with this cartoon shown here. It has 12 rows and 6 columns, so it's 72 qubits in total. If everything goes well in terms of gate fidelity, we feel this is something we can use to achieve both quantum supremacy as well as first and second order error correction for service code. And also, we think this is a very good starting point in terms of trying to try some near-term applications. And this is an image of the actual device. The central part of this gray chip is the actual qubit chip. Unfortunately, you cannot see the actual qubit because it's flipped. And the red chip here represents the control wiring, where we route all the wires in order to control the chip. And if you look very closely, you can see those launching pads where you can connect the control wires. I'm sure many of you might ask the question, what is going on with this chip? Unfortunately, at this moment, we're really working hard to get meaningful data for you. So hopefully we can update what's going on with this chip in sometime near soon. All right, so that's all about hardware. What's more important for us actually, or even harder for us, is what are the near-term applications we need to try for those devices we have built. This is a major focus for our theory team, but what I would say is not just the focus for us, it's a focus for many theorists in the community as well. For that, I would encourage you to read these two papers. One is the comments we sent to Nature by our group, and also John Preskill earlier this year published this nice review paper, give you a long list what you can give a shot on those near-term devices. In Google, what are the two algorithms we are really focusing on material simulation and optimization. For material simulation, or you can think about quantum chemistry, the algorithm we have been focusing on is so-called variational quantum eigensolvers. Some people call it VQE. It's a hybrid algorithm. In other words, you just run some quantum evolution on your quantum processors, and then you measure the outcome, and then you use the classical optimizers in order to evaluate the outcome and give you a suggestion what to try next in terms of control parameters. We feel this is a very nice algorithm because all you have to do is just run very shallow circuit, which is favorable for us, and then use a classical optimizer to help you in order to find out what is the optimal control parameters. So this is the algorithm we feel we can use to control the energy of certain molecules. In fact, we have given a shot back in 2016 using just a simple 2-qubit system to compute the energy for the hydrogen molecules with the data showing on the right. And you can compare, if you compare the red data with this black curve, the algorithm works really well. You can see that the actual experiment outcome fit really well with theoretical predictions. What's more important than that is there has been a huge progress in the algorithm in terms of material simulation. So on the left here, I show you what is the gate depth you need in order to simulate a certain molecule, say, that contains n orbitals. The n here represents the number of orbitals for that molecule. So you can see the scaling have gone from all the way from n to the 11th all the way down linear in n. This is a huge progress in the sense that imagine you're trying to simulate something around, say, 100 orbitals, which is actually a pretty meaningful molecule. The time you need to run on those sequences on the quantum computer has gone from the age of the universe all the way down to a fraction of a second. So we got really excited about those recent progress on the algorithm because we feel this is something we can give a shot, even on the size of 100 physical qubit, which is the system we're trying to build. All right, so that is about material simulation. Another application we have been focusing on more, in fact, is optimization. Optimization happens every day in your life, so it's very important. In a very simple physics language, you can think about just, we're looking for the global minimum, in this case, D point here, in a very complex energy landscape. The three algorithms we have been looking at are quantum annealing, quantum assisted parallel tempering, and quantum approximate optimization algorithm. Quantum annealing perhaps is the most studied algorithm in the community, not just by us, and well-studied algorithm in order to solve optimization problem with quantum computers. In fact, if you have enough money, you can buy a commercially available quantum annealer from this company called D-Wave in Canada. This is, in fact, what we did back in a few years ago with Google. So Google theorists actually bought a D-Wave machine and really spent a lot of time trying to test this machine. What we found out is that if you design your problem just right, so we design a very crafted problem that is most favorable for D-Wave annealer, the so-called Wickstrom network cluster problem. And we found out that D-Wave actually performed really well. If you look at the plot I'm showing here, you can see the blue curve here is D-Wave. You can see a huge speed up in terms of the time to solve this particular problem. It performs much better than simulated annealing, which is the red curve, and quantum Monte Carlo, which is the green curve. In addition, we found out that the reason we can see this huge speed up is coming from the fact that D-wave actually can have quantum. In other words, the computational resource inside D-wave of quantum annealer is incoherent quantum tunneling. However, that's not the end of the story. Just recently, those series have published this paper on PIA. They try, instead of those like generic algorithm we try in terms of QMC and symmetry annealing, they try all kinds of different other classical algorithms. Especially if you look at the three curve on the bottom here, you can see the D-wave, the most bottom one with the dark blue color. However, if you compare with those special tailored algorithms, they're classical, but they're special tailored. And you can see that if you look at the scaling in terms of this slope, actually, these two algorithms, SS and HFS, actually perform better than D-wave. In other words, we really don't see any speed up in this case for the D-wave annealer. So how to make that useful? How to make quantum annealing actually useful in terms of solving optimization problem? The biggest challenge actually coming from we need to improve the hardware. In terms of the hardware coming from many aspects, you need to improve the coherence, you need to improve the connectivity, and you also need to improve the control. This is, in fact, internally we also launched this effort to build our own annealer. We're trying to build a small system in terms of annealing, and such that we can try to see whether or not we can address all these issues. If you go to another extreme, if you have a very coherent system, the story can be very different. This is something we have been looking at in our theory team. We found out if you have a very coherent system, you can have something, a physics phenomenon we call coherent population transfer. This is something very nice. You can think about, instead of have like hopping tunneling, which is incoherent tunneling, now you have band tunneling. Or you can think about quantum diffusion. This is coming from the fact that whenever you get stuck at this local minimum, actually whenever you turn on the quantum fluctuation in terms of transverse field, you can hybridize this local minimum to other energy, to other state which has similar energy far away. Once those bands form, actually you will find out the information can quickly spread out within those bands. And our series has proved the speed for the information to spread out within those bands can given by this equation. And from this equation, you can see that we actually can see a Grover-like speed up coming from this factor 2 right here in the exponent. So this is really nice. So to fully take advantage of this phenomenon in order to solve optimization problem, this is the reason we propose this quantum-assisted parallel tempering algorithm. It's an algorithm that needs both classical processors and quantum processors. The classical processors just basically take care of all the cooling process. In other words, you can run your favorite algorithm, anyone you like, such that you can quickly move down your energy from high energy all the way down to low energy until you're stuck at those local minimum. Once you're stuck on this local minimum, what you have to do is turn on your quantum processors and hybridize the energy level, and such that you can quickly move your population back and forth within the band. By doing that a couple of times, you can quickly cool down your system, move out, cool down your system, move out. Eventually, you'll reach the global minimum, and you found a solution. What's more important that is this algorithm that, in fact, is very generic. You can either run on the analog annealer, or you can run on the gate basis level. Both of them will work just fine. And finally, I want to quickly mention this algorithm called quantum approximate optimization algorithm. It is, again, a hybrid algorithm. It's very similar to VQE, as I mentioned earlier. In other words, you need to run a quantum evolution. In this case, the quantum evolution contains the cost function itself. Once you measure the cost function, you can feed into the classical optimization process itself to give you a new suggestion in terms of control parameters. This is very nice in the sense that you don't need to run a very long sequence. If you think about digitized adiabatic quantum computing, which is very far down in the road, you can run this with very shallow circuit, which is very favorable for us in the sense that we can give a shot on those near-term devices, such as Bristol Cone we have built. And this is also the only algorithm we have known so far, which give you guaranteed process with certain number of trial steps for certain particular problems. And this performance can be improved if you keep increasing the depth of your circuit. And finally, I'd like to make sure I don't excite you too much in order to, in terms of using quantum computer to solve optimization problem. What I really want to emphasize is that the optimization problem is classical. We're trying to use quantum computers to solve a classical problem. Sometimes it's not as effective as you thought, because classical algorithms are really good. So please don't expect any quantum supremacy on all of 100 qubits or even a few hundred qubits. But that doesn't mean it's not useful. It's very useful for us to understand, to take this opportunity to understand whether or not you can actually see a scaling speed up and how this speed up scale as number of qubits. And also we can compare the performance for two different approaches. For example, annealer versus gate model. And also there's a lot of unknowns we really don't know, and it's hard to simulate classically, for example, like noise. But I also want to emphasize, don't take my message as a negative. That doesn't mean those things are not important. In fact, internally, we think this is probably the most important application we should look at for near-term devices in terms of quantum computing. So please spend your time looking at those three algorithms and help us to move on in this direction. And finally, I want to spend one slide to talk about software. So internally, we have also spent a lot of time to build the so-called quantum software. But to be honest, I really think this is classical software to help you to better use quantum computers. We have Open Fermions, which is a package to help you to compile gates for quantum chemistry problem. We also have Cirq, which is a package working at the lower level to help you compile the gates and send to quantum computers. It's like an interface. And we also have Open Fermion Cirq, which is a hybrid of these two, which specifically help you to compile gates for quantum chemistry problem and send to quantum computers. And I want to emphasize that they are complete open source, so please feel free to download all these packages to your laptop, your desktop, and try it out. We welcome you for any contributions or collaborations you can think of. Just go try it out and submit your code if you have any. And finally, I want to come back to conclude my talk with emphasis that I'm really speaking for a group effort for more than 30 people. They are wonderful scientists as well as hardware engineers. And we feel lucky to work in Google because Google really encourages you to engage a lot in many ways with academics in terms of research. We have many ways to help you in terms of research, no matter in terms of funding or quantum computing access or faculty award, or even host your sabbaticals, host your PhD student as intern, or even give your student fellowship for their pursuing their PhD degree. So if you have any good idea or found out our work is interesting, come to visit us. Remember, we're in this beautiful Santa Barbara city. It's really nice. For that, I'd like to conclude my talk, and thank you for your attention.
Thanks for that really nice talk. We have lots of time for questions.
Yes. Hello, and thank you for your interesting report. I just wanted to double check how many qubits in your newest processor are actually entangled between themselves. Thank you.
How many?
How many qubits are entangled in the processor, in the superconducting processor?
The system we have built is 72 qubits.
Right.
We do believe all the qubits can be entangled if you know enough gate depths. But what's unknown here is what is actually the gate fidelity for each pair of the qubit. This is something we have been working on at this moment. So I cannot give you the exact number at this moment. So in principle, you can run 2-qubit gate on any pair of qubit with nearest neighbor interaction.
So same question from this processor. Have you used the GMO technical in this processor, or just the a traditional XMO in this?
This particular processor is just traditional XMO, but
So
we're also working really hard to scale up GMO chip as well.
Yeah, because I think if you use the traditional XMO neighboring coupling, maybe the ZZ coupling, the residual ZZ coupling will affect your gate fidelity. Is that true in this chip? The ZZ coupling, sigma Z coupling.
Yes, that is definitely true. So yes, Gmon chip has an advantage. You can actually have more tunability in terms of coupling. That is definitely one of the major efforts we have been focusing on in terms of hardware development.
Okay.
We are building a larger Gmon chip as well.
Okay.
Yeah.
Okay. So, but technically, building a Gmon chip with a large number of qubits is difficult than this one. Is that true? Because you need more. Okay. More control line. Yeah. Okay.
Yeah. For Gmon chip, yes, definitely true because you need definitely roughly 1.5 number of lines, 1 times more number of lines in terms of controlling. Yeah, so you sacrifice a little bit number of qubits with more controllability. Yeah.
Okay, thank you.
Yeah.
Some more questions? All right, if there's, oh, there's one here.
Thank you. I want to know, do you have use some feedback technique to your chip?
Depending on the algorithm you want to try. For example, both VQE for quantum chemistry, as well as QAOA, those are the algorithm you actually need feedback. So in other words, you run quantum evolution on the chip, you measure, and you send to the class computer and analyze. Based on the outcome, you feed back to the quantum computer, to quantum processors, such that you know what is the next control parameter you should try. So yes.
You mean hardware feedback?
What?
You mean hardware feedback or just software feedback?
Yeah, those are those no FPGA. Those are things you don't need to like really fast feedback. So you can just send to classical computer like a laptop.
Okay.
Yeah.
Thank you.
Hello. I want to ask if this 72 qubits, the gate fidelity of 2 qubit is similar as the 9 qubit, or
on the few pairs we try, we can say yes.
yes.
However, this is the largest system so far we built. We actually don't know whether or not we can achieve all these across the whole entire chip, because this is the first time we build this. So we are working really hard to fully calibrate this system to tell you whether or not we can have 99.5 everywhere. So this is something we don't know.
Okay,
Yeah.
Thank you.
We have time for one or two more questions if anyone has. Okay, if not, let's thank you again for this nice talk.